All right, it's recording. Good. All right, so welcome back to the set theory seminar after the small break that we had. Our speaker today is Paul Gorbov from the University of Gothenburg, and he's going to speak to us about the Copernican multiverse of sets, and this is very much related to my own work, so I wanted to hear this talk for a very long time. All right, Paul, go ahead.
Thank you. First, just three perspectives on set theory. We can think of it as this axiomatization of a certain conception of sets, iterative cumulative conception. In this conception, we can motivate large cardinals and so on. We can also think of it as a foundation for mathematics, which is just one particular of many possibilities. But of course, the one that has been very standard, and I mean it's quite easy to use as well. And then a third perspective is to think of it in this multiverse kind of way, that basically you do maybe forcing, you do inner model constructions, going from one universe to another. Is this still loud enough? You can hear me?
Yeah, I think it's good.
Yeah, okay, good.
Mm-hmm.
What I did in collaboration with Graham Lee is to extend the setup with further axioms to make it a theory of the multiverse. So further axioms and further language. So in particular, it has this relation that we call mod. It's similar to the models, the defined satisfaction relation, the models relation that we're used to. But this is now a primitive relation that's added to the language. And so we read this mod u comma sigma as sigma is true in u. So sigma will be a code of a sentence. You could choose your favorite implementation of formal languages in set theory, but standard ways is the one familiar from Gödel in arithmetic. And then there's also a question of, okay, what are the universes, of course? And these are going to be essentially models, but we can restrict the domain in various different ways. So sort of heuristic behind this work is displayed in this picture. The idea is that if you have a multiverse, you have many universes of sets. Well, you're interested in relating these universes. One is a forcing extension of another, and so on. This involves mathematics, right, taking place. You basically need an ambient universe to situate all of these universes in, to be able to manipulate them in the usual mathematical ways. You might have embeddings and functions between these universes, and that they should live somewhere as well. So the multiverse begs for a universe to situate the universes in. But when you have a universe, then that universe begs for other universes to account for inner models and forcing extensions. So that begs then for a multiverse. So there's this circular motion here, and there's a philosophical question of what is what is the absolute background? Should you stop at having this absolute level with the multiverse where you just have all of these universes, or do you stop at some universe and have that to be absolute somehow? And our point of view here is that there is no absolute background. Yeah, we really try to take this as just a reality that we have basically this circular motion. Guiding question through the work is like, when you have a background universe in which the multiverse is situated, how does the background universe then relate to the internal universes? So this leads us to what we call the Copernican Principle. And the idea here is that the background multiverse theory, I just for the moment abbreviate this as BMT, should not hold a privileged position over the theories of its internal universes. So one way of capturing this formally is to add this deductive rule of necessitation to the background multiverse theory. So we can think of this as a closure property on the background multiverse theory that says that if the multiverse theory proves sigma, then it should also prove that sigma is true in every universe. If it does not satisfy this, then the multiverse theory will be proving things that do not hold in every universe. So then the universe of this background multiverse theory will be special. So this is the idea by the Copernican principle, that the universe of the background multiverse theory should not be special. It should be, it should represent all of the universes, basically. So the theory should not exclude any of the universes. In some sense, any universe should be a candidate for being the background universe. The multiverse theory should not exclude any universe, basically. Yeah, that is the basic idea. Yeah. So I think I should pause here, and throughout the talk, I'm happy to just be interrupted and take questions, and but especially here, I feel it's important that that you understand what I'm saying.
Paul, actually, I have a question. So about so what you're axiomatizing is a model of set theory in which the other universes live as inner models or as sets, or
as sets. Yeah. So yeah, we will get to the formal.
Okay.
Yeah.
Okay, I see.
Yes.
And as sets of any size, basically.
Yeah.
Okay. Okay, thank you.
Yeah, I'll move on. But we can come back to this stuff. So okay, the storyline then. I will. This talk is two parts. So the first part will be today, and that's basically explaining the Copernican multiverse. It's an axiomatic, untyped theory of truth for the multiverse. And the next talk will be about showing how this gives us a technique to make more or less arbitrary multiverse conceptions Copernican. So the idea is that this is not a particularly exclusive notion, but I mean, a multiverse conception may need to be tweaked. But the idea is that this is quite a general technique presented here. So basically, it's a technique for, you could say, constructing models of a Copernican multiverse. Okay, so let's get to the theory. So we have the language L is essentially the language of set theory, but since we will be dealing with sentences and syntax, it's convenient to also have a term calculus for the syntax. So that's what this plus Gödel coding machinery refers to. So for example, there will be function symbols for conjunction, for example, a binary function that takes two sentences and returns the conjunction of those two sentences. And then L-mod is the language which adds the predicate uni, which intended to say that U is a universe, and then the relation mod, where mod U, sigma is intended to say that sigma is true in the universe U. And here it's important that sigma is allowed to also be a sentence in this language L mod. So that's what we mean by that this is an untyped notion. And of course, the L mod on the first row is the meta language, and on the last row here is the object language within as defined within the theory. And,
so Paul,
yeah.
So sigma is a sentence in like a code for a sentence. So it's not, you can't talk about like truth of a formula with some free variables. You don't allow that. You only do this for sentences. Is that right?
This is, I've just simplified here in the slide. So the way we do it is as a ternary relation with so it's U, sigma, F, where F is a variable assignment. So yeah, so phi.
Oh, okay.
Yeah. So we do it for in general for formulas. Yeah.
Okay.
Okay. So first I will go through some semantically motivated theory in this language, and also some optional axioms. So primarily this involves compositional axioms and this rule of necessitation that encapsulate the Copernican principle. Then I will talk about how, so we can, the interpretation of uni, here the idea is that can basically be freely chosen to match your multiverse conception. So the extension of uni is just the universes. So you're very free here to choose whatever models basically you want to be your universes. And then the interpretation of the mod relation. This is constructed through a revision semantical process. So this is something that is well known within axiomatic theories of truth, and it's related to the Friedman-Sheard theory of truth. But it goes back to Gupta, who did some philosophical idea for using this to resolve the liar paradox. All right, so let's get to some axioms and rules then. The base theory is set up. We extend the separation and replacement to also hold for formula involving the new language. Okay, so here we have this axiom multiverse setup. This is saying that every universe setup is true in every universe. Okay, so there are two ways that you could write this axiom. One way is as a schema, where you would have one axiom for every axiom of setup, and just writing this for that axiom, and then just taking the Gödel code of that axiom in the mod relation. but there's also the sentence version where you quantify internally over ZF. And it's the latter one that we have chosen. So that is the path that we have taken. But basically our general lemma can easily be applied to the version where you choose a schema here instead. So we can talk about these two options, but the one I'm following here is the sentence version, which is stronger. And here are the compositional axioms. So these are basically just the same conditions as the Tarski conditions on satisfaction in a structure. So nothing fancy there. It's just that here we are treating this as axioms, and the mod is a primitive relation. And we have the necessitation and co-necessitation rules. You can think of this as closure properties on the theory. The necessitation I already talked about. It's this encapsulating this Copernican principle that if so here I'm actually restricting to sentences sigma. If sigma is provable, then it's provable that it holds in all the universes, and co-necessitation is.
Sorry, can I ask, is multiverse ZF, should I read that as a schema or as a single formula?
Yeah. So I talked a bit about that. So it's there are two options, and we have chosen the sentence version, so the stronger version. And but basically our whole theory, our whole machinery and techniques apply equally well to the schema version. So, but it's the sentence version that we have done in the paper and that I'm following here.
So I got confused about this point also, because if I understood you right, you said that the universes are sets. So it seems that the sentence version is the only reasonable one because you're quantifying over objects in your universe. How would it be a schema here?
Well, the schema version would be saying, so for every axiom of ZF, you would have the axiom.
Oh, I see. I'm sorry. I completely misunderstood. Yeah, I got it. Sorry.
Yeah.
Perfect. Thank you.
Yeah, it's a good point, and I'm glad we clear up this question. Yeah.
So I still didn't quite understand. So you're saying the version that you do use, which is stronger, is sort of quantifying over all subsets of U. Yeah, is that the idea to avoid using schemas?
No, it's just quantifying over all axioms of ZF, internally, and it's just saying that.
Oh, I see. I see. So it's
satisfies every axiom.
It's the internal versus the external version of ZF, because if a model is non-standard, you're asking for more if you want the universes to satisfy it. I completely missed this initially. Sorry.
So you're quantifying over all natural numbers, but that might be a non. Obviously, there's nothing to say that those are the actual natural numbers. They could be right. I think that I got.
Okay. And then a couple of extra optional axioms, but that make some sense. Non-triviality, saying that there exists a universe. It makes some sense if it's going to be a multiverse theory. But then there's a stronger axiom. This is a schema, which is saying that if every universe, so it's a schema over sentences, sigma. So if sigma is true in every universe, then sigma. So basically, then we have sigma in the background universe as well. So this is also, approaching this central question, which is what is the relation between the background universe and the internal universes? So if sigma holds in all the internal universes, then it also holds in the background universes. What this is saying. So it's very similar to the co-necessitation rule. The difference is that here it's an implication, and it's only the base language that sigma ranges over. So this sigma is not allowed to contain this mod relation, whereas the connec is a rule instead. It's not an implication. It's not an axiom. But on the other hand, it's more general in the sense that it quantifies over over the whole language, including the mod relation. And this necessitation, co-necessitation rules, they are analogs of the rules that you have in the Friedman shared theory of truth. So we're following sort of the approach taken there. And just a comment that if you have non-triviality and this multiverse ZF axiom, then that means that there is a model of ZF. You can prove that there's a model of ZF, so you can prove that ZF is consistent. So that's when you have the sentence version of the multiverse ZF axiom. Then you can prove that ZF is consistent. But if you only have the schema version of multiverse ZF, then you don't get that conclusion. Because then you cannot prove that the universe is a model of ZF. Okay, good. So moving on to give some intuition, warming up a bit in this theory. This is explaining how this necessitation rule works. So here it's the multiverse ZF axiom that is being necessitation is being applied to. So we consider that U naught is a model of CM plus necessitation. Well, then the multiverse ZF axiom, which is just written on the second line there, is also satisfied by U naught. And then by necessitation, this is also satisfied within each internal universe. So you have this situation which I'm trying to display here in the picture, that U naught contains this green universes, and then this U1, it also contains these red universes. And what I'm proving here using necessitation is that the U1 is also, it satisfies ZF, and then also U1 satisfies that U2 satisfies ZF, and so on. So you can keep applying this necessitation and get that as far down as you go, you will have that it's satisfied, that it's satisfied, that it's satisfied, and finally satisfy ZF. And so similarly, we can play this game with the non-triviality axiom, which says that there is a universe. So then U naught will contain a universe U1, and then U1 will also contain a universe U2, and so on. So here we already get the situation where we get this infinite descending chain of universes. Every universe will contain a universe. So So this really gives the kind of picture that whatever universe you look in, that will contain a non-trivial multiverse within it as well. So the universes themselves are really multiverses. And so the idea in the Copernican principle is really that it shouldn't really matter from what perspective you look at things. Of course, different universes can have different properties, but the multiverse theory should not be biased, basically. Yeah, so that's the idea. So when the background multiverse theory proves that there is a universe, then the Copernican principle entails that, well, then it also has to prove that every universe contains a universe, and you can just repeat this. Okay, so here's just a brief interlude, because we're dealing with an untyped notion of truth, meaning that this mod relation applies also to formulas that are themselves in this extended language and can use the mod relation. So this gets us into the similar kind of liar style issues that we have in theories of truth. So we have that, in particular, that these two schemas are inconsistent. So the first one is inconsistent over Cn plus nec, and the other one is inconsistent of Cn plus nec plus non-triviality. So both are basically incompatible with, having a multiverse. And this untyped T axiom. So the last axiom I showed previously was this multiverse reflection. So multiverse reflection is just the same as that, but restricted where the quantification is restricted to L. When we allow formulas from or sentences from the whole language, then we get this inconsistency. So in both cases, we use the same liar sentence, but yeah, there are different arguments. And now I realize that I have introduced this true box notation, and a simpler way to put this liar sentence is that lambda is equivalent to not true box lambda. Okay, so this puts some limits on what we can do. Okay, coming back now to the main line. So I'll start by showing how to construct an interpretation for the predicate uni. So we shall consider a collection uni K of models and a theory Tk, and they are recursively constructed like this. Okay, so this will now be used to interpret this theory that was Cn plus necessitation plus non-triviality. So you saw in non-triviality that we got that there is a universe, and that universe contains a universe, and so on. And since we also have that each universe satisfies set F, it basically gives us iterated consistency. So we are going now towards interpreting that theory in some more familiar theory. So we consider here the hierarchy of theories, which is the iterated consistency of the setup. And here I'm taking the uni predicate to just range over all of the models of the corresponding theory. And then in the theory of omega iterated consistency over ZF, plus I just artificially add a constant which refers to a non-standard number. Then I interpret uni by uni sub d for a non-standard d with this property that we have the consistency of the d iterated consistency of ZF. So there is such a d in this theory that we're considering here, this con omega plus the existence of a non-standard number. And yeah, so this is the interpretation for uni we can choose. And so what happens then in this picture is that we have that U naught satisfies that U1 is in this uni D, so the D iteration of the uni predicate. So recalling here how this is defined, it's just all of the models of the D iterated consistency of ZF. So basically it's just saying that U1 satisfies the D iterated consistency of ZF. And then also U1 satisfies that U2 satisfies the D minus 1 iterated consistency of ZF. So now you can see that since D is non-standard, we can do this omega many times. So we are getting basically this similar picture that we were getting before with using necessitation on the non-triviality axiom. Yeah, so that's to this stage. I just give that kind of intuition how this kind of interpretation goes on. Okay, and then we look at the model predicate. How is that going to be interpreted? Well, we can actually start with a more or less arbitrary formula for the 0th level. And then we revise that formula in this way. So actually the way we do it in the paper is that we just define this by Gödel fixed point formula that turns out to be really the way that you need to do it. But I think it's intuitively best to think of this as a recursive process. And right, so this is really the kind of the heart of the whole thing. And this is what we call a revision semantical process. But this process is actually quite distinct from the revision semantical process used in the axiomatic theories of truth that Friedman shared, and this tradition back to Gupta. So it's would be difficult for me to go into all the details of that, but basically what's going on here is that this is an in that case it's the extension of the truth predicate that is being revised. So you're basically considering a model of arithmetic, and you're taking just you're starting with an arbitrary set, let's say the empty set, and that's going to be the extension of the truth. And then you revise that, so you get a new extension and a new extension and so on. But here we're not working with extension, we're working with the actual formula. So we're starting with mod 0. We don't know anything about the extension of mod 0. And then basically this mod 0 is being plugged in to get mod 1. So here it's the intention that is being revised. So that's an innovation of the paper. And so, yeah, it's easy to just read off from the definition that as soon as we get off the ground, we are generalizing the usual satisfaction relation. And so now we do the same kind of thing in column omega plus there is a non-standard number. We interpret mod by mod d for also a suitable non-standard d. And then we get this theorem that Cn plus non-triviality plus necessitation, that proves con omega of ZF. That is something I already explained. Basically, non-triviality plus the multiverse ZF axioms give you that you have a model of ZF, and so you have con ZF, and then applying neck, you have a model within the model, and then you get iterated consistency, so that's quite natural. And then by the interpretations I showed here, if we also have a non-standard number, we can interpret this multiverse theory.
Excuse me, what does the C do? N less than C less than omega?
Yeah, the C is a constant that you can think of as referring to a non-standard number.
Why is it? C looks standard to me.
Ah, okay. Yeah.
Sorry.
Sorry. Yeah. It's C for constant, I guess.
See, can I ask a question also? In the same direction but lower. Here and in the definition of what the universes are, there's a quantification that says for a non-standard D, here it says suitable, before it said more specifically, such that consistency overspills, at least as far as D.
Yeah.
How do you, if you, for an interpretation, as in item B here, how does the interpretation express the non-standardness that's involved there?
Right. So, okay. So this theory that's doing the interpretation, it has this C, which is a non-standard number.
Yes.
And then you can define this number D in the theory.
You can define.
Yeah, it's going to be definable. Yeah.
Wait a minute. Yeah, I don't see how you can say D is non-standard. Within,
Yeah,
you can say it's somewhere near C, but just to say it's
okay.
doesn't.
Okay, so let's here where we have the more specific D.
Yes, this is the one I want. So the last part is fine, the con sub con D of ZF. I see that's expressible. It's just the non-standard.
Yeah. So right. So yeah, you can do this overspill argument here.
Yes,
And,
so it will be a non-standard D. I agree with that. Yes.
Yeah. And we have the C. So you know, if the C would also satisfy this condition, we could use that one.
Yes.
If not, then take the largest natural number below C that satisfy this condition.
Okay. Okay, good. Thank you.
All right, so now let's do the same exercise for multiverse reflection. So now we're going to use a different theory then, a different hierarchy of theories. In this case, we use this proof theoretic reflection schema. So we have for every sentence sigma that if the previous theory proves sigma, then sigma. So we iterate this schema. And as our extension for the uni k, it's the same as before. We just take the models of this theory. And now, unfortunately, it's not so simple to just do this overspill argument, because in the case of just consistency, we just have one sentence and then we can do overspill, but we cannot do overspill on a whole schema. So instead here we only get local interpretability. And so I will close today's talk with then giving the general lemma that you can, these results are applications of that general lemma. So here I'm giving now the definition of what we call revision parameters. So that's basically what you take for this hierarchy of theories and collections of universes and your starting mod 0. These are the parameters. They just have to satisfy some very basic conditions. Basically, these theories have to be subtheories. They are stronger the further you go up the hierarchy. Yeah, it's this is not something I really need to dive into. But then we have this revision rules. So these are now the basically what you need to get this necessitation and co-necessitation on the theory. These are the closure properties now considered in this hierarchical way instead. So I would ask you to just focus on the lower bubble here and just understand these revision rules. And then we get to the main lemma. So similarly, as you've seen, the interpretation is going to be to interpret this uni by uni t and mod by mod t. So then this italicized it denotes that interpretation. Yeah, so the main lemma is saying this, that if we have revision parameters that admit this next star and co-next star rules, and you know the theory that we start with is satisfies set F, and then we have, so let F be a family of interpretations. So this particular family of interpretations that is written here. So K is ranging over the natural numbers, and yeah, so IK is interpreting uni by uni K and mod by mod K. And then we can let S be any theory, which also might be in this extended language with union mod. And we have for every finite subtheory that eventually TK proves the interpretation of that gamma. Then we have the limit of the hierarchy locally interprets ms plus s, which is the cm plus s plus nec plus conec. So it locally interprets it by f. So I mean that for some, so for any finite subtheory of ms plus s, there is a k such that ik will interpret that in T omega. So yeah, so in the this lemma you can use them to prove that the two things I've already gone through. So in the first case, S was just a single sentence saying that there is a universe, and then the interpretation of that will be then that there is a U satisfying uni sub k, and then uni sub k was just saying that there is a U such that U is a modulo of kth iterated consistency, and that is satisfied by tk, which in that case was kth iterated consistency theory. So yeah, maybe yeah, you have to shift by one or something like that. There might be some indexed thing there, but basically I think that should give the basic idea how the lemma works. And for the multiverse reflection, then S is the whole schema of multiverse reflection. And then it makes sense that you need this to consider this gamma, this finite part. And then yeah, similar proof works. So this is the result, one of the results that required considerable work. And basically the idea is that this lemma then gives the technique. You can give, so it's very general in the sense that you can take these hierarchies or these revision parameters T uni mod 0. It's a hierarchy of theories and corresponding universes. You are very free in how you choose these parameters. So basically, if you have a multiverse conception where every universe is well-founded, or every universe is countable recursively saturated, which are very different conceptions, it's completely fine to put this in here as parameters. Right, so that was the end of today's session. So yeah, happy to take questions. questions, of course, comments.
Okay, thanks very much for your talk, for this first part of the talk. Any questions before I ask mine?
Quick question. These iterated consistency statements, con k+1, which sort of go back to Turing. I think Turing had a paper, the first paper on this kind of thing. Is it necessarily basically the original sort of simple meta language, countable language, or can you actually play games with infinitary languages or other extensions of the standard of standard languages as you iterate these consistency statements?
I'm not actually familiar with iterating consistency statements for infinitary languages, so I can't really say anything about that. I haven't really thought about it. It's I think it's in general it would be interesting to think of infinitary languages for this kind of truth in the universe and the truth for the multiverse with infinitary languages makes sense to look at.
Yeah, the infinitary language come up often in the recent seminars as tools for the extending universes and for characterizing them. Work of Sheila and others, so they might be relevant.
Right.
Anyone else?
Could I ask a follow-up question to what I asked before? So you pointed out that you can just, if the overspill doesn't reach C, you just take the largest D that it does reach, and there's the D you want.
Yeah.
So if you have a universe with that D, then because it sees the consistency of the previous theory, the universes within that U, the next smaller level, will have D-1 as the extent of the overspill, and that's exactly, as far as I can see, that's exactly what you want. But then what worries me a little bit is that if D is even, D-1 is odd, and these universes and sub-universes and so on can use that to detect modulo 2 how far they are below each other. In other words, they don't really have the same opinion about everything. One of them thinks overspill reaches to D, reaches to an even number. The other thinks it only reaches to an odd number. Is that ever going to be a problem?
Well, I think it's I mean, it's not a problem, you know, for interpreting this necessitation rule.
Mm-hmm.
So the way that we formulated the Copernican principle, it's not a problem. I don't know if maybe, I mean, if you just think of the Copernican principle as a philosophical principle, then it's more like open to interpretation what it should mean. And perhaps this is not something I've thought about, like, but you know, maybe you could cook up some argument using that. But in general, I think, yeah, this, you know, even, odd, this I think is something that could be interesting to look into, because it's part of the expressive power of this system that you can do those kind of things.
So essentially, it's no problem for you. You're saying it's no problem for your theory, and I would add that then if it's a problem at all, it's a problem for my intuitive picture to go with it.
I see. Yeah. Okay.
Okay.
Right. I see. Well. Okay.
I mean, theorems are theorems, regardless of what my intuitive picture is. So.
Yeah. Well, I think okay. So maybe to help your intuition, I think it's a difference between the semantics and the theory. So it's the theory that's supposed to be neutral.
Okay,
And of course, as soon as you take a model of the theory, then it's not going to be neutral. It's going to be just a special model. And so it's when you have a model, then you can start looking down into the model, you know, into what universes does it contain and so on. And you're picking some specific one, and then you can talk about even and odd and so on. But the theory itself just gets passed down each step. And yeah, so yeah, that's really what my intuition is saying, that's where this should be resolved, I think.
thank you.
Anyone else? Okay, so I guess the general question that I have is, of course, our intuition is that among the universes, there should be sort of the usual, the forcing extensions, the various inner models. What ensures here that this is going to be the case? I think I missed this somehow.
Right, so yeah, so what I've been saying is that you're free to take pretty much whatever you want as your extension of uni, as far as I've been talking here. And so this really applies to a great variety of multiverse conceptions, but it turns out that it harmonizes well with, you know, Hamkin's multiverse conception, basically, and the model construction that you and Hamkin's made, and that's I will get into in the next session. So that's a more sophisticated axiom than this multiverse reflection that we talked about here. Yeah, I can just, I guess, briefly show that axiom. So that's called self-perception. So here we're saying that actually there is a universe in the multiverse that is isomorphic to the background universe. So L-isomorphic, not to the extended language. That's impossible, but L-isomorphic.
I see.
And so that will really get us into that kind of multiverse. But yeah, our paper does not concern itself at all with what axioms uni should satisfy. Basically, that's kind of the idea, that this should be applicable to any multiverse conception.
Okay, thank you. I think that helps. Anyone else? Last chance before I stop recording. Okay, Paul, thanks very much again for this really interesting first part. I'm very much looking forward to the second part next week, especially with that introduction that you just done. All right, so I'm going to stop recording at this point. Okay.